If the sun has an atmosphere, then it has weather, and understanding solar weather is going to be fun because it involves interesting physics. It's going to be important because it actually affects life on Earth, and so let's try to understand in what way solar weather is very, very different from the weather here on Earth. And so the indication of solar weather are these blemishes, these spots on the sun. First known recording of these is in the writings of a Chinese astronomer, whose name I can only pronounce as Gande. Galileo observed the sunspots and used them to find the rotation period of the sun. The sun rotates about its axis, moving from west to east every 25.4 days. This is a medieval depiction of two sunspots on the surface of the sun. These sunspots appear as dark spots on the sun. Here you see a modern image of the sun with a few regions of sunspots. They appear dark, as we said, because they're cooler than the surrounding. At the center of a sunspot, the temperature can dip as low as 4,000 Kelvin. Because of T to the fourth, they emit less. And if you remember that the sun is approximately 100 times the radius of Earth, then the typical size of a sunspot is about the size of Earth. And it was the observation of Wilson in 1769 that, in fact, by watching the behavior of sunspots as they approach the edge of the visible disk of the sun, that they're in fact depressions in the solar surface. This is what a sunspot looks like when magnified. This is an Earth-like region which is cooler than the surrounding. The central part of the sunspot is called the umbra. The less dark exterior is called the penumbra. Although shadows have nothing to do with it, the words are completely borrowed. So what are these things? And hints to the fact, to the origin of these things, come by observing the patterns of their formation. It turns out that sunspot number varies with a very nice 11-year cyclicity. This famous butterfly graph here on the right indicates, well, on the bottom, we see the number of sunspots, or the total fraction of the solar disk's area covered by sunspots, as a function of years from somewhere in the 1800s all the way through to the present day. And we see that there's this periodic oscillation, lots of sunspots, then none, and lots of sunspots, then none. And when you look more closely at where along the sun they're generated, that's what the butterfly graph above shows us. This is sort of a picture of the vertical axis is latitude along the sun, and we see that early in a cycle, sunspots are created at mid-latitudes, and then as the cycle proceeds, they're formed closer and closer to the equator, and then there's a whole bunch of them at the equator, and then they all disappear, and then there's a break, and then some more sunspots form at mid-latitudes, and slowly they move towards the equator, and the pattern repeats. It's hard to see in this graph, but in fact, 2010 was the end of a very abnormally long solar minimum in which there were no sunspots, and nobody understands exactly, as far as I can tell, what the cause was for this reason. Now, an important discovery is that we can associate sunspots to magnetic regions of strong vertical magnetic fields on the sun. So magnetic field poking out of the surface of the sun, and the way you measure this is because it turns out that a magnetic field has an effect on the spectrum of atoms in the presence of a magnetic field. You can measure the shift in the absorption lines that we saw in the sun spectrum. It's all by looking, and we can therefore measure the magnitude of a magnetic field. And this is a magnetic field map. Again, we have the lines of latitude and longitude along the sun, and as a function of time, we see that when there are lots of sunspots, there are a lot of these regions of high magnetic field. Notice that yellow is one polarity and blue the opposite polarity, so magnetic field pointing in and out of the sun, and the sunspots appear in pairs. You see regions of blue preceded by yellow in this rotation, so there is a blue dot, and then to the west of it, a yellow dot in the northern hemisphere, and the polarity is reversed in the southern hemisphere. And this is consistent throughout a cycle, and in the between cycles, the polarity reverses, so that if the blue dots, we don't have two cycles here, but if the blue dots were ahead of the yellow dots in the north in this cycle, and the yellow ahead of the blue in the south in this cycle, this would reverse from one cycle to the other. And this is our hint that what drives these sunspots is in fact a magnetic field. It turns out that what makes them cool is that, remember when we talked about the Van Allen radiation belts, we said that regions of strong magnetic field repel charged particles. The upwelling gas coming up to the photosphere from the interior regions is charged. Magnetic field, intense magnetic fields, like in the sunspots, choke off this convection, and for that reason the interior of a sunspot is cooler than the surrounding part of the sun, down, as I said, to 4,000 Kelvin. And so we understand sunspots as a magnetic phenomenon, and the fact that the particles in the atmosphere are charged and therefore interact strongly with the magnetic field, as are, by the way, all of the particles in the interior of the sun, plays an important role in understanding both the causes of this phenomenon and some of its consequences. So we're led to look to the solar magnetic field and try to understand that and see how that drives the weather. The magnetic field of the sun is not quite as simple as that of the Earth. It's not well described most times, like a bar magnet with a north and a south pole, although at any time there is roughly a north and a south pole, and it is roughly aligned with the axis of rotation. The big difference is that in the interior of the sun, the roiling, convecting fluid that presumably generates the magnetic field is not just conducting but charged. It's a plasma. And you recall when we talked about the interaction of the solar wind with the Earth's magnetic field, that I said that because a stream of charged particles both is influenced by a magnetic field but also creates a magnetic field, we can imagine we have a situation where magnetic fields and charged particles are strongly interacting, and we can model this by imagining that the magnetic field lines and the particles are tied to each other. So if we have a weak current like we had in our tube, the current is trapped around the magnetic field. But if we have a stronger current, it can drag the magnetic field around, which is what the solar wind did to Earth's magnetic field, and is what the rotating plasma in the interior of the sun does to the magnetic field. And a crucial ingredient in this is that the rotation period of the sun is not uniform, like in the case of Jupiter. The sun experiences, as a fluid body, it experiences differential rotation. The sun's rotation period is 25 and a bit days at the equator, but 29 days at the pole, so that the equator rotates faster than the pole. This has the following effect upon the sun's magnetic field. So here's the rotating sun. It's undergoing differential rotation. You start with a sort of a dipolar magnetic field, but the magnetic field lines are trapped by the plasma, and because the equator rotates faster than the poles, the magnetic field lines are stretched so that you get, first you started with a north-south magnetic field, then you ended up with an east-west magnetic field, and these field lines are stretched, and these stretched field lines are kind of like rubber bands. They contain large amounts of magnetic energy, and this releases by the field sort of reconnecting, popping out of the sun's surface, creating all these bubbles. And these might remind you some of the structures we saw when we looked at coronagraphs. Remember that if magnetic field lines poke out of the sun, then the charged particles trapped along them will spiral along the magnetic fields and form loops of charged particles, and these are the prominences that we saw. And what happens is that this process of winding up the magnetic field until it's energetically favorable to reconnect, and the sun's field becomes a mess for a while, takes about 11 years. And so every 11 years, the sun's polarity, in fact, reverses. You start with the nice polar magnetic field that we started with, and then you wind it up, you produce a mess, and the mess reinstates a polar magnetic field with the opposite north-south polarity after about 11 years, and the pattern repeats itself. This is the cause of the magnetic cycle and of the creation of sunspots. So sunspots are these regions where the magnetic field lines poke out of the sun and in, and their orientation in each hemisphere is due to the direction of rotation relative to the direction of the magnetic field, and this reverses between cycles because the polarity reverses, and we get a big vertical component where these arches poke out, and at the bottom of the two base points of each of these arches sits a sunspot. So the most active times in the sun's magnetic history are the times when the field is in the process of reversing. These reconnection events release the magnetic energy stored in these magnetic fields. I told you that you could treat them as rubber bands. They snap back, they release a lot of energy. The local release of energy in a reconnection event can be on the order of 10 to the 25 joules. This leads to rather dramatic solar flares, where one region of the sun suddenly becomes very bright and emits a lot of ultraviolet and X-ray light. In these beautiful ultraviolet images, you can actually trace the outlines of those magnetic field arches that I spoke about. That's not because we can see the magnetic fields, but because we see the ultraviolet emissions from the charged particles that are trapped along the magnetic fields. It's very kind of these particles to give us such an indication of the fields. So solar flares are energetic events. There are far more violent events that go on. They're called prominences or coronal mass ejections. And here is a collection of views from many NASA observatories of a coronal mass ejection that occurred a few months ago. This is an event in which an amount of hydrogen and charged particles on the order of the mass of the Earth is ejected at high speed as magnetic pressure basically builds up and ejects these charged particles at high speed. This one was not directed towards Earth. When such events happen and are directed towards Earth, this is these periodic sudden increases in the intensity of the solar wind that cause beautiful aurorae, but also can cause disruption of communications as the electronics in communication satellites is injured by this stream of charged particles. And so this is why we have so many different observatories observing the sun at many wavelengths from many angles in order to be able to understand these phenomena, if possible, predict them, and certainly give us the 3-day warning. 3 days is approximately the time it takes one of these coronal mass ejections to get from the sun to Earth, and getting the 3-day warning allows satellite operators to sort of shut down operations in an orderly fashion and not allow damage to happen to their satellites. And so we've developed a pretty decent understanding of how the sun works as a star, both in terms of the internal energetic and energy production, and in terms of the structure of the sun itself. Our job now is going to be to try to extend that to nearby stars. And the first question we're going to have to ask is, how far are these things? Because anything we see needs to be interpreted differently depending on how far it is. And so our first chore is going to be to measure distances to stars. And it's to that we'll turn next.